text document, which is a massive text document. And from that, they can rasterize, compress the model, and from that, we can get our different measures of structural complexity and rugosity. So from that program, there are multiple different structural complexity measures you can choose from. These are the ones we went for. So first off, we went for two-dimensional rugosity. So this is a relatively simple measure. It just takes into account the peaks and dips along the reef structure in a single vector. For this one specifically, we took an average of 4 5-meter transects to get a good indication across the full transect. The next one is three-dimensional rugosity. So almost the exact same measure, but this time done over a full area. So you've got multiple vectors, and this was for the full 10-meter by 2-meter transect. So up a level of complexity for this one. Then we jumped up an even higher level of complexity and looked at fractal dimension. So this metric is at a much higher resolution. And the easiest way to explain this one is it essentially looks at patterns within patterns and how complex those patterns are. So it's squiggly, squiggly, squiggly. This goes beyond just peaks and dips. It measures all those different points, patterns, plots them in a logarithmic scale, and the structural fractal dimension is taken as the slope of the best fit curve for that power curve. And again, this was done over the full transect, 10 meters by 2 meters, so it's full spatial area. So what do we get? So from our, all the different transects we did, out of the 14, 11 were successful, and they all looked a lot like this. So let's dive into some of the close-ups from this transect to see how much it really worked. So first up, you can see individual oyster clumps. So this is really high resolution, which is very exciting. It also very successfully captured our reference objects, which are golf balls, because all golf balls are the same size. This let us set the scale for the model in the structural complexity calculator. We also picked up things like this Cosastra, so it even picks up mobile and sessile organisms living on the reef. The only part I had a little bit of tricky with was clumps of filamentous algae. So the structure there is still captured, but maybe not to the highest resolution as we'd want, which is understandable when filamentous algae is as fine and probably was moving when the photos were taken. There we go. So our main results from all the different measures from the three, we found that fractal dimension was the most significant when compared to Shannon Weiner's species diversity. Which is just great to see such a strong positive relationship. The other structural measures, so 2D and 3D rugosity, were not significant compared to fractal dimension. But we think that the fractal dimension, the way it is measured, is taking into account different spatial scales of refugees in the covered 2 centimeter to 20 centimeter organisms. It was much more representative than from the 2D and 3D rugosity. What we can say overall is that the photogrammetry works on such a low vertical relief habitat, such as an oyster reef, and has applications in restoration for long-term monitoring as the restoration progress goes along. To enhance this, you could even have a permanent transect, so you could measure the same area of a reef over time as it is undergoing recovery. And it can recover indications for both reef structure and species diversity. There you go. So thank you very much for listening to me today. I've got 2 of our other publications up there if you want to scan the QR codes, and I look forward to your questions.
Are there any questions? Yes, there's one over there. There's one over there. So thank you, Naomi, for this wonderful presentation. One of the main questions I have is some of your photogrammetry, I have to learn a new word today, they didn't succeed in producing a good file. What was the main reasons why they didn't succeed and the other ones did?
So the ones that didn't work, you mean?
Exactly.
There's just gaps. So either due to the photos that were taken or the water visibility. 'Cause we're in Scotland, so sometimes our water visibility drops down to 2 meters. Yeah. Not fantastic for this sort of survey. One of the modifications we tried to get around that was reducing the depth that we were taking the survey at. So generally speaking, it's advised you're 2 meters above the seabed. We dropped down to 1 meter. But even then there was, a couple that just weren't great. So I didn't want to put them through the model and get weird data from them.
Yeah, so it's just in-field conditions that dictate whether they work or not.
Yeah, or technical problems as well.
Thank you so much.
Is there still time for another question? Ev, is there still time for another question? Because there is one here.
Yeah.
Hi, thank you for the presentation. Actually, I have 2 questions, but maybe I'll... so, how did you do the scaling? That's the first one. Maybe I missed it. And the other one is the resolution model that output.
So for scaling, the point reference objects I used were golf balls. They're about roughly 4 to 5 centimeters. 4 to 5, not 45. In the software I used, which was Mushroom, you're able to input that data, and you're also able to input it to Gwydion. So for that, I was able to scale the whole model. For Gwydion as well, when I was taking the overall area, I was able to input the very specific size area that I wanted. So for that reason, I didn't trim down the models, because I knew I could do it in Gwydion. For the resolution question, I'm not quite sure, just in terms of like pixel constraint.
Maybe you can discuss that during the lunch break.
I don't have the detail off the top of my head.
Okay, thank you very much. So our next speaker is Abel Zempleni from Le Mar and Ifremer in France, and he will tell us a bit about biodiversity on oyster reefs.
Yes.
Please go ahead.
So, hello everyone. I'm Abel Zempleni, working to a second-year PhD student and working at Ifremer in France, in Brittany. And so here I will present one part of my thesis, which is an exhaustive analysis of all the fauna associated to remnant oyster populations in Brittany. So, as you all know, I think, this figure, oyster reefs, when healthy, they have quite some ecosystem functions, and so ecosystem services that derive from them. And here I will be concentrating on biodiversity enhancement, which is considered as being one of the most important ecosystem services of oyster reefs, of healthy oyster reef. So here's a little definition given by Moebius in his book of the oyster and oyster culture from the 19th century. And so there is this whole definition, and with other parts of this definition, it's based on that he actually suggests a new word for all this associated fauna, which is biocenosis, and so we still use this word to this day. So that's quite cool. That is based on Australopithecus reefs. And now let's fast forward 200 years, the Native Oyster Restoration Monitoring Handbook. And so in this monitoring handbook, there are 4 metrics that are for biodiversity. So these biodiversity metrics, metric 19 to metric 22. So in faunal invertebrates, so these organisms that are in the seabed underneath the oyster bed, metric 20 on epifaunal and sessile invertebrates, 21 on small resident fish and mobile invertebrates, so these are vegi species, and then transient fish and crustaceans, so bigger fish. And yeah. So for our study, we have 3 studies that are 3 historical oyster beds in Brittany. So Bonduroz, which is in the Bay of Brest, in South Brittany, Banc du Belon, and in North Brittany, Banc de la Rance. And so here is the list of the metrics that have been sampled and that have been followed during this year in these 3 sites. So as you can see, unfortunately, it's only on the Banc du Rose that we have all 4 metrics. So let's concentrate on that for now. So this site is has a depth of 3 to 8 meters according to the tides, and it's a little bit different from the others because actually the oysters are sitting on a marl bed, which is already a very biodiverse and rich ecosystem, also an engineering species, and so it's a quite restricted area with a density of 1 to 10 oysters per square meters. We have oyster aggregates, we have individual oysters, so yes, and which is good for the oyster that it's in the Natura 2000 zone, so all fishing and dredging activities are prohibited. And there are restoration actions that have been implemented at this site since 2017, and that's the work of Stéphane Pouvreau. So, you know it. So let's check all the different biodiversity metrics that we've sampled this year. So here's our sampling schedule. And so for metric 20, which is epifaunal invertebrates, we did a seasonal sampling, so spring, summer, autumn. Then for vegi species, so small resident fish and crustaceans, it was a monthly sampling. And then for transient fish, it was more or less a daily sampling throughout this whole period with cameras. I will talk about it later. So the epibiotic community. As I said, we had 3 samplings, only 3 because we consider that this community is maybe more stable than the other one, so a seasonal sampling might be enough, and also because the analysis, so the taxonomic analysis of all this is the most time-consuming one. So at each sampling date we had 10 aggregates, so these oyster aggregates made from dead and living oysters directly picked from the seabed. And we had like from 5 to 10 oysters or oyster shells in it. And then they were picked by divers and conserved in a formulated solution at 4%, and then analyzed to the species. Everything was analyzed to the species, everything bigger than 500 micrometers. So it's a taxonomic analysis. Here you can see that I added data from spring 2023, which was my first sampling campaign and my first work in taxonomy. And here that's a Venn diagram that shows the repartition of the species according to the different sampling seasons or sampling, yeah. So first of all, we had a total of 190 species only in epibiotic community, which is quite a lot. And as you can see, there is kind of a big difference in terms of, we didn't find the same species or all the same species between spring 2023 and 2025. We're still thinking about why that is. But yes, and so for the year 2025, from spring and summer, we had a total of 143 species that have been identified this year. And so 40% of them were seaworms, so basically polychaetes, most of them. 23% I think were crustaceans, and then 18% sorry, of mollusks, so gastropods and bivalves, and 19% others, so we have sea skirts, sponges, and other species. So yes, that's quite a lot. I'm happy with that. And I don't expect you to read this whole table. It's only to show that there is only one little star on the Simpsons Diversity Index, but all the other biodiversity metrics, there are no significant differences between the different sampling dates. But on the Simpsons Diversity Index, we have a little bit higher index in spring 2023 than for the other ones. And that may be because in 2025 we actually have a huge abundance of Spirorbis, which is a polychaete, and so we have a species that is really, really dominating the whole data set. But we will look into it later and adding also the data from autumn, from September. Let's talk about the small resident fish and mobile invertebrates, so metric 21 in the handbook. Here we had another sampling method. So first of all, it was every month, once a month. And for that, we used these oyster standardized units. We didn't invent this term. It was invented before. And it's basically a cage, so an 18 centimeter high and 15 centimeter diameter round cylindrical cage that we fill with oyster shells and living oysters directly picked from the seabed. And then we let it rest there for 1 month. So it's kind of an artificial oyster reef or a big artificial oyster aggregate. And we will wait 1 month in order it to be colonized by these small resident organisms. And once a month, it is sampled with divers with a special net. I will show you a video of how it is done. And then everything is analyzed under binocular as for the other ones. So here's the video of the sampling method with the net. So we go there, we try to catch everything, and then we can directly close the bag with a scratch. And so that, as this diver shows, for instance, here he has a goby, so a little fish that we wouldn't have been able to capture if we just directly handpicked this oyster standardized unit. So that's our protocol, and so we still have one sampling in December. So for now, we had a total of 26 species of these mobile invertebrates. So 5 fish species, mollusks, gobies, blennies, Lepidogasters, for all of those who know. 14 crustacean species, Galatea and everything. 2 species of sea worms that were different from the other ones because they are free-living polychaetes, very big ones that can swim, actually. And 3 species of echinoderms, sea stars, basically, and 2 species of mollusks. So, yes, that's what we have for now. And then the third metric, metric 22, transient fish and crustaceans. So here it's a whole other story. It's video sampling. So for that we had 2 GoPros, one for the oyster reef and one for the control zone. And here you can see our oyster reef is basically a square. So what we did is we picked oyster aggregates from the seabed and just put them in a 4 square meter square in order to create an artificial oyster reef and in order to exaggerate the effect of the reef compared to an area where oysters are just spread, 1 there, 5 there. So we wanted to exaggerate and to concentrate the oysters at one, and in order to be able to film it also. And then we delimited a control zone, so the same size, 4 square meter, without any oysters, just on the marl bed. And so between them there is approximately 50 meters. And then we deployed the GoPros. So the GoPros are programmed to take 10 minutes videos every hour, so until the battery dies. And so then divers will go, collect data, change the battery, and put the GoPro back so that we can have a quite high frequency data throughout this whole period. And we are still analyzing it, so I don't have any quantitative data, but I can show you some videos. The first one with a little action on the reef, which was pretty cool. So cuttlefish feeding and all the black sea breams just coming there. So that's our star video for now. And but yes, that's beautiful, but it's still no quantitative data. And so the next slide is just to show you our impression that we have now when we are analyzing the data between the oyster reef, where we have quite constantly fish, especially in summer periods. There are fish schools, there are mostly sea breams, black sea breams, and the control zone, there is basically nothing, and sometimes 1 or 2 fish just swimming by. So, to conclude on this whole biocenosis on oyster reefs, we had a total of 169 species on the oyster bed during this summer period of 2025. You can see between the different metrics, and I added 114 species that are different from these ones found on the oyster that were found in the marl bed, and that's a study from 2019, published in 2020, and they did this whole, for 4 years, they just followed all the epibiotic and community of the marl and showed that it's actually pretty stable throughout the years. So we consider that we can use this data in order to compare with the oysters. So thank you very much for your attention, and I would like to thank my supervisor for this. Thank you.
there any questions?
First of all, congratulations for your presentation, very nice. My question is about, talking about healthiness of oyster reef. Did you check, of course you checked all the species in the list, which was the proportion of if you have alien species? I mean, these oyster reefs are healthy in terms of biodiversity, reducing the infiltration of alien species, or did you notice any signal of invasion?
I mean, we have alien species that have been there for years now. So, for instance, the Japanese oyster drill, which is really bad because it really kills most of the oysters that are on the seabed. So, for now, I'm still analyzing the data. So, I will have to check it better. So I cannot answer that.
Okay, sorry for that.
No worries.
I don't want to stress you.
No worries. And so just to tease, we will do a whole functional analysis on this whole ecosystem also. So we'll have all the functional traits and also an analysis on invasive species or not. So,
okay, thank you.
No worries.
We have a second question over here.
Yeah, really nice presentation, thank you. I was wondering, you had 3 sampling campaigns, 2 in the spring, 1 in the summer. And there was quite a difference between the 2 spring campaigns, right?
Yes.
Did you also take into account temperature? Was there a difference in temperature in the water in these 2 seasons?
Yes, we checked it, and actually it was quite similar. So that I don't think that it's the main cause of this difference. We were thinking about different things between the 2. There was a huge storm, so Kiran storm, but it was like 2 years before, so I don't think that it would have such an impact. We don't know.
Okay.
For now.
Thank you.
How are we doing time-wise?
Is it a very quick question? Okay.
Thank you so much. What method do you use for the epiphyte sampling? I was just wondering, what did you do with the epibionts?
Epibionts?
Yeah.
Well, basically, we take the whole aggregate, so an oyster clump, and we put it in a big jar. So we conserve it with formaldehyde. It's a 4% solution. And then once we want to analyze it, we take the formal, we rinse it, everything. And then we'll first check all the oyster valves. We will measure all the oysters, and then we'll check all the valves to take all the epibionts, and then we will break all the oysters in order to have, for instance, Polydora that is dwelling in the shell, so that we can have, we hope, everything. So yeah, that's our method.
Thank you very much. Now we welcome Hailey Craig from University of Bournemouth.
Wait till it comes up. I've morphed into Zoe, I'm not Hayley. So I'm going to be talking today about our eDNA work that we've been doing on the oyster reefs as part of the Solent Seascape project. There we go. Yeah, so the Solent Seascape project is a multi-habitat, multi-site seascape restoration project focusing on seagrass, oyster reefs, bird nesting sites and salt marsh. But for the purpose of today, I'm just going to be talking to you about the scientific monitoring that we've been doing via eDNA on our active restoration of Austria edgeless reefs. So the Solent is a large body of water, about 500 square kilometres on the south coast of England, highlighted in the red square on the bottom. And every single dot on the map you can see is either active or passive restoration or monitoring sites. But all you need to know for today is those 2 red dots. The one on the left is the Hamble and one in the centre is Langston Harbour. So Barney is going to be talking more on Thursday in more detail about these reef sites, the challenges and the processes. But the Langston Harbour site was created in September of 2021 with our first baseline samples for eDNA taken in 2023, which is when the project first started. And then for Hamble Reef, actually started in March of 2023 when we also took the baseline samples. It was extended in April of 2025, and then just Thursday last week we added another 13,867 oysters for phase 3 of that reef. So there's now about 40,000 oysters on that reef. The red dot that you can see in that third picture is also where we do our seine net surveys for this site, so you can see how close we are later in the presentation. So what do we want to know from this eDNA? We want to know whether or not the restored Australoedula reef structures are producing any detectable differences in that fish community composition compared to the control sites that we have nearby. So all of our research is using a BACI control, so before-after control impact. This data is very new. We got it back about a month ago from sequencing, so it's been quite a steep learning curve when it's been coming to the bioinformatics, so I'll take you through it slowly. But before the results, I want to talk through our methods. So this is Hayley collecting our surface water samples. We do this at every single one of our monitoring sites in 3 replicates in winter and in the summer, so that's February, March time and July, August time. Once we have collected those samples, we filtered them through a 0.8 micron filter using a peristaltic pump rather than by hand, because 5 litres does take a bit of time. And once we've filtered these, we take it into our pre-PCR lab, run it through our DNA extraction, and then we run our PCRs as well as the gels. And then we send this off for sequencing. This comes back to us, and then we run it through our bioinformatic pipeline in R using the MyFish12S pipeline. So these next 4 slides are looking at Langston and Hamble as sites as a whole and comparing them to one another. This is our species list from the eDNA. So we took 96 species across 45 different families. The top 10 list is there on the left, which no surprises here really, apart from the European bullhead and the rainbow trout, which we've not seen in any of our seine net surveys. We were expecting bass, sprat and goby species. However, if you split it by site, they shared 72 species in common, with 15 unique species at the Hamble. Most of these species were freshwater species like pike, gudgeon, rudd and dace, mainly because the salinity at Hamble is slightly lower than that in Langston. We also had some very, very small reed counts of John Dory and monkfish, but I think as we do have fishing boats in the River Hamble, chances are this is probably discards from boats rather than actually being present on the reef. And then in Langston, we had 9 unique species, including brill, undulate ray, sand sole, and really nice to see the short-snouted seahorse on there. Just out of interest, I wanted to compare this to a historical analysis of these sites that I conducted earlier this year from 2007 to 2012. We've got 36 species, so almost a third less done in our manual surveys across 22 families. Our top 10 species list is there, but as you can see, there are 2 families on this list, because when it comes to identifying herring, sprat and pilchard in the field when they're 4 centimetres long is quite challenging, so it's really nice to see that the eDNA can distinguish between these species for us rather than when we're faced to the species in real life. Again, if you split this across Hamble and Langston, Hamble had 5 unique species, including broad-nosed pipefish and the rock goby, whereas Langston had 9 unique species, including garfish, plaice, lesser weaver, and sand eel. However, we've got the reverse of that at our Langston site. However, as Barney will allude to on Thursday, this site went missing, for want of better words, and this data was taken from March of 2023 when we started to blue, the blue points are handball controls, and the orange is Langston, with the circles being control and the triangles being the restoration sites. What we can see here is a really clear difference between our two sites. They're separating quite nicely. There is a slight overlap in the middle of the plot, which is mainly driven by our control sites, which was confirmed with the statistics that there was no significant difference between our control sites at Langston and Hamble. However, when you look at the outskirts of the plot, that's dominated more by our restoration sites. Again, confirmed with statistics that the reef communities between Hamble and Langston are significantly different. What was really nice to see in this is the fact that our historical data that we analysed for 12 years from 2007 also showed the same picture. So even though they are sites within the Solent, they had distinct community composition, both in our SaneNet surveys as well as the eDNA. So the DNA is a lot higher resolution, but it is telling us the same story, which is really, really nice to see. The fact that they are different means that we can analyse them in isolation rather than them having exactly the same community composition. So this picture here is that of the Hamble Reef. The wiggly red line is our rough permissioned area for our reef, and that the red dot that you can see is where we carry out our small fish survey, so it is quite close to one another. So this is our MDS plot of community composition for the Hamble. I'm going to walk you through it. So we've got in blue, we have our winter samples, and in pink we have our summer samples. The outlines around each of the things are significant groupings. So on the far left, you've got those two blue winter sites from 2023, which are our control. This was prior to restoration, so they're grouped separately on their own. If you move slowly into the middle of the plot, we've got really nice differentiation between summer and winter samples, with pink at the top of the plot and blue at the bottom of the plot. There isn't really much difference between the control and the reef in the summer of 2023 and summer of 2024. They're all grouping together. However, winter is slightly separated, especially for the reef in 2024, whereas the reef and the control are grouping together in 2023. Moving further along the plot onto the far right-hand side, you've still got that clear differentiation between the seasons, with summer at the top and winter at the bottom. But what is really nice to see is, even though there's no significant grouping for the winters between the control and the reef, as soon as we've hit summer of 2025, we've got two significant groups there between the control and the reef site. So it'll be really interesting to see how this story emerges, as this is the third year that we've sampled, and we'll be carrying on to sample next year as well. So it'd be really good to see what happens with the eDNA data in 2026. Again, this story follows what we found with our analysis on the historical data set. Season was a clear driver of fish community in that 12-year data set as well. So again, even though that eDNA is high resolution, it's still telling us the same picture, which is really reassuring. So this is quite a busy slide, but all I want to draw your attention to is the fact that it is mirroring the MDS plot that I just shared, but adding in those eDNA reads for the different species. So in the top there, we've got winter and of 2023 and 2024. There's no clear groupings there apart from season, so the years are mixing together. We then move across to the centre of the plot, which has got control and reef sites of summer of 2024 and summer of 2023. Again, not clear groupings for the reef and the control. But then we move across to 2025. There's clear seasonal differences, but we do have those really nice groupings there between the control and the reef, and this is mainly driven by the three species you can see there, which are bass, mullet, and some gobies as well. This data only came through about 3 weeks ago, so it's very, very fresh. So there's lots more things that we would like to do. As eDNA works as a presence-absence tool, really, we want to apply the trophic guilds to the data sets that we've got to see if we can work on building a trophic web of what's actually happening at the oyster reefs in the Hamble. We'd like to combine this with BRUV and video footage that we've collected, and then run this eDNA as well with our CO1 and 18S pipeline, which is benthic invertebrates and phytoplankton, and ultimately we would like to run this all through our salt marsh and our seagrass as well, and then look at this as a connected picture so we can understand the trophic webs behind each of those restored habitats and then how they work together as a connected system. So thank you very much, and I look forward to any questions.
Questions?
eDNA as well, and we want to implement that. Is the difference probably means that the controls, what would they like in terms of substrate?
They are in the solent for the handlers. What we So all of the sites where we've done the restoration, we've had to add a huge amount of mixed sediment and mulch to there to be able to enable the restoration. So the control sites, basically mud.
Yeah, I guess from point of view what we're doing, we're trying to see, we just attract this reef associated with a specific fish community, and you didn't pick up on, and perhaps more benthic, like gobies.
Yeah, I think that more, I need to have another look at the data and see which the species are driving those changes. I think that more, I need to have another look at the data and see which the species are driving those changes, potentially, because it is very fresh. But,
okay. Thanks.
Okay, thank you very much. We move on to the final speaker before the lunch break, which is Fiona Woods from the University of Southampton, who will tell us about the nitrogen remediation. Thank you.
Hi, so I'm Fiona Woods. I'm from the University of Southampton, but I've also been working very closely with Blue Marine Foundation and the University of Portsmouth. So Zoe's presentation has been a beautiful introduction to some of my work as well. So I'm looking at the impact of location on oyster-mediated nitrogen remediation, specifically at the two restoration sites that Zoe previously mentioned in Langston Harbour and the River Hamble. It's one of the biggest oyster fisheries in Europe, self-sustaining, very high yields. And then in the later 1980s and 1990s, there was a slow decline in populations of oysters, although the fishery was still very, very active and had a high economic turnover. There was a slow decline in the early 2000s of oysters, although the fishery was still very, very active, and then in 2013 had a high economic turnover. Completely crashed. In the early 2000s, there was a really sharp drop in the population, and then in 2013 the population completely crashed. Various different organisations leading the work fishing authorities closed the fishery, predominantly led by. From 2014 onwards, there have been various different organisations leading the work on restoring native oysters, as I'm sure you're all aware, has predominantly led by very big recently, with the Solent Seascape project being one of the forefront. So Restoration of Solent, as I'm sure you're all aware, has these two sites, very, very big recently, with the Solent Seascape project being one of the forefront. They are quite close together. I'm slightly different as River Hamble has much more of a freshwater input and generally has a slightly more recreational boat use on it. But when we were first starting to source oysters early in 2014 and onwards for doing the reefs in early 2020s, there's a bit of an issue because the population of oysters in the Solent is functionally extinct. So we can't really get oysters from our own area to just conglomerate them into bigger reef sites. We have to get them from further afield. So originally we started getting them from Loch Ryan, and then more recently we've been getting them from various points in Wales, especially South Wales at the moment. These sites are quite different from the Solent. On the left you can see a beautiful picture of Loch Ryan, and on the right there is Engle Bay in South Wales. Very, very pretty, not a whole lot of human impact here, not a lot of boat use, not a lot of people use. Very scenic, would be lovely to go there. In comparison, this is on the left, we have Portsmouth Harbour. It has one of the bigger Navy bases in the country. As you can see, there are 2 aircraft carriers based there, as in conjunction with a lot of other vessels, from Navy military vessels in general, aircraft carriers based there, as long as the biggest, in conjunction with a lot of other vessels, from Navy military vessels in general, to and then the biggest oil refinery, the second biggest container port in England on the bottom right, which is in Southampton, very high use and then the biggest oil refinery in the country on the top right. It's also got a high agricultural input, so lots of very, very high use area with lots of, as well as pollutants. It's also got a high agricultural input, so lots of nitrate runs. So I'm sure many of you are aware about oyster-mediated nitrogen cycling. Basically, when they are respiring and when they are actively filtering, they take in water, it goes through their system, and some of it gets fixed in their tissues, some of it gets fixed in their shell, and some of it gets deposited on the seabed as feces and pseudofeces. Now, I'm not focusing too much on the mechanics of how any of this happens, more just what happens when they do this. So I'm going to talk about 2 experiments. The first one, not so much detail, because this is what sparked the second experiment, but not long after the last NORA conference, myself, Joe, Zoe, and Monica Fabra, who's not here, has had a massive input, sat down and was like, this is really interesting. We're going to compare the Solent oysters that have always lived here, have never seen any other water, to the oysters we've got from Loch Ryan, and we're just going to see what the differences are. So we did an experiment in static open tanks in the aquarium. We had Solent oysters, and we had Loch Ryan oysters, and then we'd feed them, take a water sample, wait 2 hours, and then take another water sample and collect any feces or pseudofeces produced. We did this for 24 hours. I wouldn't recommend, but it was very interesting. So the main results from this that are nice and easy to understand is that the feces and pseudofeces, as you can see, there's a massive significant difference between the Loch Ryan oysters and the Solent oysters. And you would kind of expect this. The Solent oysters have always lived in the maybe less desirable water. They are used to it. They haven't had to adapt. However, the oysters we got from Loch Ryan had about 5 years to adapt to the water in this system. So they weren't fresh and new to it, and they still have much less carbon and nitrogen within the pseudofeces, which we did with CHN analysis. Now, the water analyses we did was a little bit more convoluted. So I haven't got a graph of it because it's a very, very confusing graph. There is a slight difference, but it's not really very easy to see. But because of this data in the pseudofeces, we're like, this is very interesting. We'll move on to looking at how the location can have an impact. So then experiment 2, we got oysters from South Wales, just South Wales, and I got them almost a year ago. There was a slight pause as we got oysters from South Wales, just South Wales, and I got them almost a year ago. There was a slight they had been waiting as we were waiting for organisations at the Portsmouth site to give various permissions and consents. So they had been waiting in flow-through tanks at the University of Portsmouth site, which is right next to Langston Harbour, as you can back out to sea on the right, basically and it's just fed with water that comes in through the basic settlement tank through and then put into the back out to sea in early April, marginally cleaner seawater. They were there for about 3 months, and then put into the sea in early April oysters in River Hamble and at Langston Harbour, and then in suspended broodstock cages, so then have oysters in River Hamble and about 200-300 metres away from the Langston Harbour, and they're in suspended broodstock cages at the restoration sites, and about 200-300 metres away from the restoration sites. So it's in both cases. Data set at the moment. So they deployed in April, and then seasonally I am taking samples, and then still doing the respiration experiment. Data set at the moment. Sampled oysters, but the sizes, the growth rate has been monitored, and then I did a respiration experiment 0 before each time we sampled oysters, and then taking oxygen readings throughout the experiment, nutrients in general in the water at time 0 before we close the chambers, and then taking oxygen readings throughout the experiment experiment at once every hour, and then taking another water sample at most due to the fact that at 6 hours in the water was and it was only too low. At the end of this experiment, the oysters are now in storage. I am doing a couple of other experiments on them, so unfortunately I haven't got actual respiration rates. I've only got oxygen consumption rates at this time. But in a few months I will have all of this, so unfortunately I haven't got actual respiration rates. I've only got oxygen consumption rates at this time. But in a few months I will have between the growth rates at the different harbours. So the results from this, there is growing much faster difference. Although interestingly, between the growth rates and the different harbours, with Hamble oysters overall growing much faster. Although interestingly, there was one consumption rate that we looked at. Now, the first baseline that I did was in April. Obviously, the water is very, very cold in April. This is also seen in the oxygen consumption rates. Now, the first baseline that I did was in April. Obviously, the water is very, very July, and the water was approximately 21 degrees. Going to be less. However, Langston and Hamble sampling in the summer was done in July, and the water was approximately 21 degrees. In the sea. These results are very warm, slightly hard to interpret. However, if we look at it as the difference between the difference in the drop between Langston and Hamble, it shows it a little bit differently, with another very significant difference in oxygen consumption rate. And again, Hamble oysters tend to consume oxygen at a slower rate to the oysters in Langston Harbour, even though they have both come from the exact same source. Oxygen at a slower rate to the oysters in Langston Harbour, even though they have both come from the exact same source. And then finally, the nutrient cycling. So this is very much a work in progress still, because I got the data back very, very recently. But Hamble, in general, had significantly higher nutrient concentrations just in the water than Langston Harbour, which was quite interesting. But Langston oysters had a more significant effect on their concentration. More, as you can see in especially the phosphates, there is minimal phosphates there after 6 hours compared to Hamble oysters. And I feel like there is minimal phosphates there after 6 hours compared to the conclusions from this is basically the site has a massive significant effect on the rate of growth, oxygen consumption, and nutrient cycling in native oysters. So we kind of need to be really, really careful when we're looking at implications for nutrient credit schemes. As if we're saying oysters can do this, there's quite often a statement goes around that they can cycle 200 litres of water in a day. Yes, probably some oysters can. Some oysters will do significantly less, and some will do probably much, much more, depending on where they have come from and where they have now moved to. So this leads to the question that maybe should we actually be moving oysters? Should we be looking more at doing maybe spat on shell or remote setting, or just trying to bolster brood stock and doing very small restoration hatcheries at sites that we are doing restoration work in, so that we can know exactly what the oysters in that site are doing. So I just want to say thank you to all of my supervisors and everybody who's helped collect this data. It's quite a large team of people. And also just to say thank you to my funders as well. I'm happy to take any questions.
Questions?
Hi, sorry, I might not have understood very well, but when you are looking at the impact on nutrients, you had an oyster in a tank and it was not flow through, it was individual oysters?
We put them in closed systems, so they are cycled with a peristaltic pump just so that the water is moving. It's basically a very rustic respiration chamber, and then the water is sampled just before the tank is closed, and then as soon as it is opened at the end of the 6 hours, and then the nutrients from that is put through an autoanalyzer to look at the different levels of nitrates and phosphate.
So it's an individual oyster?
Each oyster is individual, and then the data on this slide is the mean of those individuals, yes.
Okay. And are you feeding them?
Not during the respiration experiment, no.
Okay. And what about your controls?
So the controls, basically, the controls was the dotted line you saw on the first one for the respiration. The controls for the actual nutrient changes didn't, basically. They went down marginally. Langston Harbour or Hamble River oysters. Thank you.
There's another question.
So a good question. The short answer is I don't know. That's kind of why I did this. So with the first experiment that we looked at, the Locharayan oysters had been in the solent for 5 years. They apparently had not, compared to oysters that had always been in the solent.
Great talk, thank you. Are they generally morphologically pretty similar, in size and?
So at the start of the experiment, all of the oysters were, they were not significantly different in size, and then they were just randomly separated into either the Langston site or the Hampel site. And then the very significant differences you see after about 5 months is just factors of growth at those different sites.
Okay, if there are no other questions, well, thank you again, Fiona. So now it is lunchtime, and our session on ecosystem services will continue after lunch, so please be back here at 2:30.